All right, so we're just about ready to introduce the Grothendieck spectral sequence. I'll remind you of a few things before we do that, but by the end of this video, we will meet the Grothendieck spectral sequence. Some good references here are Weibel and McCleary, and I also found a master's thesis on spectral sequences by Orlick that really spells out a lot of the details, so that might be a nice thing to look at, and I'll try to remember to post that to the CCLE site. But in any case, I'm hoping that you thought about Hom and taking right-derived functors. But if you haven't, let me remind you. From the exercise at the end of the last video. But just in case, let me remind you. So let's say that we have some functor f from a to b. So this is going to be a left exact functor. And these should be abelian categories. And if A has enough injectives, then we can form right-derived functors of this f. Okay, and this will be exactly analogous to our left-derived functors from last time. And again, I'm going to sort of remind you of this stuff pretty fast. I'm assuming that you know it. If you don't, definitely take a look in Weibel or whatever your favorite homological algebra book is. So our sort of classic example, as I mentioned, is Hom. So let's say Hom from x. This is going to be left exact. Okay, I guess I haven't decorated that, so maybe that means abelian groups. I really probably want to work in R modules, and again, I just want to be lazy and not have to write the R everywhere. So if X is an R module, and my A and B are both R modules, or maybe when it's abelian groups, fine, then of course I can take R linear Homs. But everywhere here, feel free to put in the R. I'm going to be lazy and leave it off. But okay, so what does it mean to be left exact? That means that if I had a short exact sequence, say abelian groups or R modules, that I can apply this Hom functor, and I'll have Hom from x to a. Remember, this one's the covariant one, since I'm Homming out of x. There's, of course, the contravariant version as well, and it's also left exact, but let's not deal with that right now. Okay, so I get this sequence, and this is exact, and notice I didn't put the 0 at the end because maybe this last map is not surjective. But we can correct for that lack of surjectivity with our xed terms. So xed is the correction term here, and I've got x1 from x to a. Can't write, okay, x to b, x to c, and there's a map here making this a long exact sequence, and then of course I continue up to x2 and so on, so I get a long exact sequence. Okay, so as usual, how do we compute these higher xed terms, xi, of x with a? Well, the first thing you want to do, I don't know why I'm writing in blue, but you want to take an injective resolution of a. And remember, we saw, of course, the last time that we could take a projective resolution of x instead, but let's just do it this way. And the color's annoying me here, so I'm going to change it back. That's not even the right color. Apparently I'm using that one. Okay, really important stuff, I know. Okay, so we take an injective resolution, so that means we've got this exact sequence where A includes into some I0 that's injective, and then we map to I1, I2, and so on. So this is exact, and as as is the usual thing, you sort of cut off, we cut off here and take the rest of it, so just the eyes, and apply our functor, which in this case is hom x blank. Okay, and then we get this sequence. Okay, I know this is probably very familiar to all of you, and even if it's been a while, I probably could have just said, and dualize appropriately, but I want to make sure we're all on the exact same page when I'm talking about these functors. Okay, so I get this hom applied to my injective resolution, and then take cohomology. Or you could call it homology. I'm just calling it cohomology because the degrees of the eyes going up. Okay, and so then a short way to say that is that xi of x with A is just the ith cohomology of hom x applied to this injective resolution. And that's what we call the ith right derived functor of this left exact functor hom x blank, and we've applied it to A. Okay, so I said this, but of course, if I was working over R modules, then I would decorate this with an R, and then this is just hom in the category of R modules, x to I. Okay, so in general, back to our case where we just have some functor f, we want to do basically the same game. So in general, we had some f that was left exact. And so we take an injective resolution of our A, and the ith right derived functor of f applied to A is just take the ith homology of your functor applied to the injective resolution. Okay, so take homology in the ith spot. And we said this in the left derived case when we were talking about tensor and tor, but again, let me remind you that if I apply f to that resolution where I've got the I included, or the A included, sorry, writing I but trying to say A. Well, that was an exact sequence, and f is left exact, so this is still going to be exact sequence. And then when we go ahead and we rip this piece off, then we'll see that the 0th right derived functor, we still have that homology f of A in degree 0, so that's exactly our f of A. Okay, so another way of saying that is in our x case, x0 really is just hom. Okay, maybe just some terminology. So notice that if I look at the ith right derived functor of f and I apply it to j, I get 0 most of the time if j is injective. So for I greater than 0. And that's just because, well, I've got an injective resolution of j and it's very short, all right? And so then we can use that to define that A is f acyclic if we take that ith derived functor and we apply it to A and we get 0 for all I greater than 0. Okay, all right, so lots of maybe boring reminders. I don't know, maybe that was interesting once, but I think probably at this point, not so exciting. But with all of that in mind, then we can actually say what the Grothendieck spectral sequence is. So let's do that now. So this is a theorem due to Grothendieck, and so it's often called the Grothendieck spectral sequence. Here I want to work in the context where A B, and C are going to be abelian categories. And I want to set myself up with just what I need to be able to take injective resolutions. So we'll say where A and B, these abelian categories, have enough injectives. Most of the time in practice, everything in sight has enough injectives, so you don't really have to worry about it. But okay, got enough injectives, and now I want some left exact functors. So let's take some functors between these categories, and annoyingly different sources are going to name different ones F and G, so I'm going to make F be my functor from A to B, and then I can follow that with G. So these are left exact functors. And that's almost enough, but I need a little bit more. So we'll say such that F takes injective objects to G acyclic objects. Okay, so of course, injective objects are F acyclic, and we want to make sure that the output of those is G acyclic. So to me, that kind of feels like something about saying the composition is zero in a sense. That's really in a very loose sense, but okay, so then finally, what do we have? Well, the claim is that there's a first quadrant spectral sequence. And remember, those first quadrant spectral sequences are nice, that everything sort of stabilizes at some point. So these are good spectral sequences. And the E2 term we can identify using the right-derived functors. So we'll take the pth right-derived functor of G, applied to the qth right-derived functor of F, applied to A. And what does this converge to? Well, the claim is that we get the right-derived functors Rp plus Q of the composition, G after F, and again applied to A. All right, and there's also a dual version, though in practice, the spectral sequence is very important in algebra and algebraic geometry. It shows up a lot. And for whatever reason, maybe just I'm not an algebraic geometer, and so I could be mistaken about this, but for the most part, I see people refer to this version where we have some left exact functors and we talk about their right derived functors. And I suspect that has to do with sheaves and some examples that we'll see in people's presentations. But you can also prove a dual version just as well. So here we'd want to use left derived functors. Okay, and then I'm going to write almost exactly the same thing. So I basically just replace those R's with L's, but we've got to make all of the necessary adjustments. So again, I'm going to have 3 abelian categories. And now I want A and B to have enough projectives. Well, of course, I use projective resolutions to compute left-derived functors, so that makes sense. And then we'll set things up in exactly the same way. So I have some functor f from A to B and some functor g from B to C. And now they should be right exact, so like tensor. And remember, we needed something nice about the composition. So the analogous thing is that F should take projectives, which will be F acyclics, to G acyclic objects. Okay, I probably didn't need to write all of this out. I could have just said replace injective with projective to do the obvious things. But I think it's kind of nice for concreteness and ultimately just to have in your notes to easily refer back to that then you get a first quadrant spectral sequence that people tend to grade homologically. And we take the left pth derived functor of G and we apply it to the left qth derived functor, qth is a weird thing to say, of F, and we apply that to A. And that's what our E2 page looks like. And then what does that cook up for us? Well, it converges to the left derived functors of the composition. Okay, so again, these are particularly important in algebraic geometry, though I tend to see this one for the right derived functors much more. And I want to talk a little bit about some applications and also how we get this spectral sequence. So for example, you might remember that I said at some point that a spectral sequence for a double complex is a special case of a spectral sequence for filtration, and we saw that. We can filter that a double complex by rows and columns, giving us a filtration of the total complex. And then I also said the Grothendieck spectral sequence is a special case of that. So we should be able to come up with some nice double complex and see this spectral sequence arise from it. Okay, so this is what we'll do in the next few videos.